Now, let us look at these limits. This is the general expression for the response yt for any given x tau, any given x t. So, however, when we talk about causal systems, special case of causal systems and causal signals or causal inputs. If we take that, then what are the consequences? If the system is causal, then an impulse x delta tau given here cannot have an impulse response for negative values of time. That means h t will be 0 for t less than 0. So, if the system is causal, the impulse response must be 0 for negative values of time. So, the consequence of this causal system is h t is 0 for t less than 0. If the input is a causal input, that means x t is 0 for t less than 0. Because of these two restrictions, this impulse, this convolution integral that we are having here minus infinity to plus infinity, these limits can be now be simplified, because x tau is going to be 0 for negative values of tau. We need not start the integration from minus infinity, you can start from 0, right. Similarly, tau is a running variable. When tau exceeds t, then this h of t minus tau, the argument becomes negative, therefore that is going to be 0. Therefore, this integration need to be carried out only for up to tau equals t instead of infinity. So, these lower limit and the upper limit can be reduced now to 0 and t, then we can write x tau h of t minus tau d2. So, for the special case of a causal system with a causal input, we need to carry out this integration only between the limits 0 and t, not between minus infinity to plus infinity. In particular, if x t for example may have an impulse at the origin. So, we must take that effect of the impulse into account. Therefore, it would be advisable for us to start the integration from 0 minus, so that that impulse is fully taken into account in our calculation. Similarly, the impulse response may have an impulse at the origin. It may be possible that if you given an impulse, then there may be impulse present in the response also. That means h of 0 may also have an impulse. Therefore, to take that into account, you can take this to plus. So, 0 minus and t plus are taken to account for impulses at the origin in x t on one hand and h t on the other. If you know such impulses, then you can always take the 0 and t, but if you have impulses present, it is advisable to take from 0 minus to t plus. That is how it goes. So, to summarize this discussion up to this point is, given the response of a linear time invariant continuous system to an impulse, we describe this h of t. H of t is called the impulse response. This gives complete information about the system to enable us to calculate the response to any input. And so, any given input x t can be regarded as a summation of several impulses, as we have taken like this, and each impulse gives rise to a corresponding response, which can be calculated in terms of the impulse response. Putting all of them together, we come to an integration. Y of t is given by this integral, which is called the convolution integral, and the meaning of convolution we have seen. And in particular, when we are talking about causal systems with causal inputs, the limits need not be from minus infinity to plus infinity, as it would be in a general case, but in the particular case of these type systems between 0 to t. In particular, we may have impulses at the origin both in h of t and x of t. To take care of them, you must take the integration from 0 minus to t plus, otherwise only half the impulse will be taken into account. Now, let us work out a few examples to illustrate these ideas. Let us take an example to illustrate the idea of convolution. Let us take a general function f of t, try to convolve with delta t and see what happens. So, you have two time functions, and since the final convolution is a function of time and you are doing some integration, it would be advisable for us to involve another variable, a dummy variable which gets integrated in the process. So, let me say that this is tau and this is f of tau, f of tau. Now, delta tau is this. So, delta minus tau is also the same thing because it is an even function. So, if you fold it, it becomes the same thing, delta tau. So, that means delta tau is now here, delta minus tau, and in order to, what is it that we want to do? We want to take f tau delta t minus tau d tau and you want to integrate that. So, instead of delta tau you must take delta t minus tau, that means this we must take delta minus of t minus tau, tau minus t. That means you must advance this delta by an amount equal to t. So, if you want to calculate the product the convolution at a value t, you shift it by an amount. So, this will be delta t minus tau, where this is the value t. So, this shift depends upon the particular value t which you want, at which you want to evaluate. For 1 second you shift it by 1 second, if you want to evaluate at 2 seconds you shift it by 2 seconds, and so on and so forth. Now, you have folded this signal, then shifted this signal, then multiply these two out. If you multiply these two out, you have f tau multiplied by delta t minus tau. What you get is, because delta is 0 everywhere else except at this point, you have a small delta here whose value is f at the value t delta t minus tau. And when you integrate that, f tau delta t minus tau, that will be equal to the area under this curve is f of t. So, the result is that f t convolved with delta t is f t itself. Answer is f of t itself. This is a very interesting result, that the delta function when it is convolved with any time function yields the same time function identically without any change. It is something like what you may, of course you may not have delta in practice, but if you have a narrow slit, for example, instead of a delta function, suppose you are having a small slit like this and you do the same convolution, then you get an output which is very closely resembling this f of t. Something like you are, for example, the soundtrack on a film passing through a sensing head, or a sound signal on a tape passing through a head. Then if you have a narrow slit, when you pass it through this, and if a response is something like similar to the product and then integration over that small area, then you get more or less essentially the same signal as the output, something similar to that. Now, let us take a second example. Let us see what happens when a step function is convolved with another step function, u of t convolved with u of t. So, the result is, suppose the result of this is called g of t. According to the formula, this will be u tau, u of t minus tau, that is the second signal, d tau, and you integrate that over the limits which are appropriate to this. Let us see what they are. Now, you take first of all u tau, this is u tau, this is 0 here and this is equal to 1. Now, u of minus, to take care to picturize this, u of tau is like this, u of minus tau will be something like this. This is u of minus tau. But then you do not want u of minus tau, you must shift it by an amount equal to t. U of t minus tau would be something like this, that will be u of t minus tau, where this amount is equal to t. So, you multiply these two, this is also equal to 1, this is multiplied by this, you will get this curve 0 to t. So, the area under this curve, after all when you want to integrate this, it means you are finding out the area under this curve. The area under this curve is t. T units. Therefore, the result of ut star with ut or the convolution of that is going to be t for positive t. So, we can say this is t for t greater than 0 because we have shifted in the forward direction. Now, let us imagine what happens for negative t. This is for t, what you have pictured here is for t greater than 0. What happens when t is less than 0? So, this is u tau, this is u of minus tau. For negative t, you shift it in the other direction. Therefore, you have a curve like this, that will be u t minus tau for t less than 0. So, when you make the product of these two curves, it will be 0 because when this is non-zero, the other is 0. When this is non-zero, this function is 0. Therefore, the product is 0. Product of u tau times u t minus tau is going to be 0 identically, therefore, area is going to be 0, therefore, the convolution product is 0 for t less than 0. So, the product is described by r of t, that is a ramp function. That means ut star, it will be like this. If it is 1, this is 1. So, the conclusion is ut convolved with ut equals r of t. So, the idea of convolution is relatively easily seen in simple cases by plotting these graphs in this manner. Again, the key words are fold, shift, multiply and integrate. Integrate means finding out the area under the curve. For simple geometries, the area under the curve can be easily found out without doing integration, and you can picture what is the final result is going to be using these concepts. Now, one more example. Given h of t for a type of system that we are talking about is 2e to the power of minus t minus e to the power of minus t ut for an initially relaxed linear time invariant continuous time system, find response to a ut b e to the power of minus 3t ut. So, that means we are asked to find out using this impulse response the response to two arbitrary inputs. Now, let us see the first one. If u of t gives rise to a response a t, then a t can be found out by convolving u of t with the h of t. So, I will write this as the input now is ut and that is convolved with the impulse response h t. So, the meaning of this would be both are now this is a causal system, the impulse response is 0 for negative values of time, and the input is also causal. Therefore, we can straight away say this is 0 to t ut. So, I will call it u tau h t minus tau d tau, right. Then this can be regarded as 0 to t. In the interval 0 to t, when tau takes from positive values, this is going to be 1 anyway, therefore, we can disregard this. So, h we can write this 2e minus of t minus tau minus e of minus of t minus tau d tau. Again, u tau is there, u of t minus tau is there, u of t minus tau is going to be 1 in the interval from 0 to t, because as long as tau is less than t, then t minus tau is going to be positive. Therefore, both this u tau here and u of t minus tau that is coming here are going to be 1 in the range of integration, therefore, they can be omitted. So, this will be what you are having here, and this can be written as you in the integration e to the power of minus t comes out for the first term, therefore you have 2 e to the power of minus t, and then when you integrating of e to the power of, I'm sorry, there is some mistake here. I should have put this minus 2t, kindly note this, therefore this is minus of 2 of t minus tau, otherwise there is no meaning in writing two things, 2 minus t minus tau. Therefore you have e to the power 2 e to the power of minus two t and 0 to t e to the power of tau d tau, that is one term, and then minus e to the power of minus t, that is a common factor that comes out, e to the power of tau d tau 0 to t. You can carry out these two integrations and final result will be e to the power of minus t and minus e to the power of minus 2t. This is valid for t greater than 0. So the a of t is now obtained as, answer is e to the power of minus t minus e to the power of minus gt. That is the answer as far as the first part is concerned. Yeah. The second part, the yt is now 0 to t again, u tau, not u tau, this time is e to the power of minus 3 tau, that is the input. This is going to be one for the range of integration, ht minus tau, that is 2 e to the power of minus 2 t minus tau minus e to the power of minus t minus tau d tau. That is the integration that is to be done, and working out as before, this is the integration with reference to tau, therefore e to the power of minus 2t can be brought outside, 2 e to the power of minus 2t, then 0 to t e to the power of minus 3 tau and e to the power of minus plus 2 tau, we have got e to the power of minus tau d tau. And then for the second part, you have e to the power of minus t that can be pulled outside, and the integral from 0 to t e to the power of minus 3 tau and e to the power of plus tau, therefore e to the power of minus 2 tau d tau is what you are getting. And if you carry out this work, the answer will be finally minus 3 upon 2 e to the power of minus 3t plus 2 e to the power of minus 2t minus e to the power of minus t upon 2 for t greater than 0. Of course, for t less than 0 it is going to be 0. Notice that in this particular case we have found out the complete solution. After all, the input now e to the power of minus 3t, that means the forced part of the response will have only this particular complex frequency which is equal to minus 3. So this is the forced part of the response. This is the response which you would have obtained by taking the particular integral solution of the differential equation. And this part is the natural response which contains the response when there is no particular inputs, no sustained inputs. Actually, as a matter of fact, as you can see, the impulse response, what do you mean by impulse response? An impulse appears at t equals 0 and afterwards there is no input. That means whatever follows is kind of natural response of the system. Therefore, the impulse response here, whatever frequencies are present here are the natural frequencies of the system. And the forced response will, for e to the power of minus 3t, will have also e to the power of minus 3t. So that you can recognize this to be the forced response of the particular integral solution, and this is the natural response or what comes from the complementary solution of the differential equation. So at this stage, let us summarize what we have done so far in the question of introductory system concepts. We have seen how systems can be analyzed, particularly the transient behavior of systems. We have looked at various methods, the classical differential equation approach, which entails a lot of involved calculations to find out both the complementary function as well as the particular integral solution, and even more so finding out the initial conditions in a differential equation of a large order. Then we said equivalent information of the differential equation can be obtained through the system function concept h of s or to the frequency response function h of j omega. We will exploit these two particular functions in when we are discussing the Laplace transformation and Fourier transform techniques at a later point of time. We also said that equivalent information can be provided by the impulse response method, impulse response h of t, or the step response a of t. We have looked at some detail only the impulse response as far as our previous discussion goes. A similar analysis can be given in terms of the step response as well. Step response is called a of t, as we have mentioned here. Almost identically we can carry out the analysis. We have also some kind of convolution integral involved there also, but we will do this later after we study Laplace transformation methods. So impulse response and step response also can be used to characterize the linear system, and here again we are calculating all this in time domain only. So these are all different ways of describing the input output relations of a linear system. The differential equation approach, the system function approach, both as a function of s, both as a function of j omega, or in time domain using either the impulse response or the step response, sometimes called indicial response. The step response is also called indicial response. Some of these techniques we will return to later when we are talking about Laplace transformation techniques. And so we will close our discussion of the introductory system concepts at this stage. Let me now give a set of examples for you to work out in the form of an exercise.